Welcome to aiRobot. I am Kishore Kumar Vaja. In this video, we will learn how to build GAN using Keras. One of the most important deep learning advancements of recent years is generative adversarial networks, simply called as GANs, have the potential to build next generation models as they can mimic any distribution of data. Major research and development work is being undertaken in this field because it is one of the most rapidly growing areas of machine learning. Generative adversarial networks are a type of deep neural network architecture that uses unsupervised machine learning to generate data. They were introduced in 2014 in a paper by Ian Goodfellow, Joshua Bengio, and Arun Korville. So, what is a GAN? A GAN is a deep neural network architecture made up of two networks, a generator network and a discriminator network. Through multiple cycles of generation and discrimination, both networks train each other while simultaneously trying to outwit each other. Generator network uses existing data to generate new data. For example, it can use existing images to generate new images. The generator's primary goal is to generate data such as images, video, audio, or text from a randomly generated vector of numbers called a latent space. While creating a generator network, we need to specify the goal of the network. This might be image generation, video generation, audio generation, text generation, and so on. Discriminator network tries to differentiate between the real data and the fake data generated by the generator network. The discriminator network tries to put the incoming data into predefined categories. It can either perform multi-class classification or binary classification. Generally, in GANs, binary classification is performed. So, the discriminator network is a classifier and is slightly different from the generator network. This discriminator processes an image and outputs a probability of image belonging to a particular class. Let's see some practical applications of GANs. Image generation. Generative networks can be used to generate realistic images. Image generation is used in marketing, logo generation, entertainment, social media, and so on. Text to image synthesis. GANs can generate images from text descriptions. This can be helpful in film industry, comic industry, and it is possible to automatically generate sequences of a story. Face aging. This can be very useful for both entertainment and surveillance industries. It is particularly useful for face verification because it means that a company does not need to change their security systems as people get older. HCGAN network can generate images at different ages, which can then be used to train a robust model for face verification. Image to image translation can be used to convert images taken in the day to images taken at night, to convert sketches to paintings, and many more. These use cases are groundbreaking because they can save our time. Video synthesis. GANs can also be used to generate videos in less time. High resolution image generation. GANs can help you generate high resolution images without losing any essential details from low resolution images. They can be useful on websites, completing missing parts of images, drug development, and many more practical applications. GANs have certain advantages over other methods of supervised or unsupervised learning. GANs are an unsupervised learning method. GANs don't require labeled data. They can be trained using unlabeled data as they learn the internal representations of the data. GANs generate data similar to real data. Because of this, they have many different uses in the real world. GANs learn density distributions of data. They can learn messy and complicated distributions of data. This can be used for many machine learning problems. The trained discriminator is a classifier to classify objects. There are currently thousands of different GANs available, and this number is increasing at a phenomenal rate. In this video, we will learn about building a deep convolutional generative adversarial network architecture. But now, essentially, all GAN architectures contain convolutional layers, so the DC is implied when we talk about GANs. And these DC GANs were the first GAN model to learn to generate high resolution images in a single shot. DC GANs are able to generate high quality images when trained on restricted domains of images such as images of living rooms, bedrooms, etc. GAN is a battle between two adversaries, the generator and the discriminator. The generator is defined by a differential function g that takes random noise z from the latent space as input and uses parameter theta g. Then generator produces a fake image g of z, and the discriminator is defined by a differential function d that takes real images x and fake images g of z simultaneously as input and uses parameter theta d. And it uses supervised learning technique to predict whether an image comes from the original dataset or it is one of the generator's forgeries, that is fake image. The generator is trained to fool the discriminator, and the discriminator classifies the samples as real or fake. To succeed in this game, the generator must learn to make fake samples, that is indistinguishable from real samples. Formally, GANs are a structured probabilistic model containing latent variables z and observed variables x. These two networks are represented by these two differential functions g and d. Each of which is differentiable with respect to its inputs and with respect to its parameters. The goal of the discriminator is for the real image samples d of x to be near 1. For the fake image sample g of z, the discriminator strives to make d of g of z approach 0. But the generator strives to make the same quantity approach 1. If both models have sufficient capacity, then the Nash equilibrium of this game corresponds to g of z and d of x equal to 1 by 2 for all x. Both these functions g and d have cost functions j that are defined in terms of both network parameters theta. The generator wishes to minimize cost function j of g in terms of network parameters theta of d, theta of g, and the generator can control only generator parameter theta of g. The discriminator wishes to minimize cost function j of d in terms of network parameters theta d and theta g, and the discriminator can control only discriminator parameter theta d. Because each network's cost depends on the other network's parameters, but each network cannot control the other network's parameters. The discriminator's cost function jd with network parameters theta d, theta g is equal to minus 1 by 2 of Ex of P data into log of d of x plus Ez into log of 1 minus d of g of z. This is just the standard cross-entropy cost that is minimized when training discriminator with a sigmoid output. What is the solution if the optimization problem occurs? The solution to an optimization problem is a local minimum, that is a Nash equilibrium. It is a point in parameter space where all neighboring points have greater or equal cost. In this context, a Nash equilibrium is a tuple theta d comma theta g. That is a local minimum of discriminator cost function jd with respect to parameter theta d and local minimum of generator cost function jg with respect to parameter theta g. Let's first take a look at how we build the discriminator. It consists of 4 convolutional layers, first 2 having 64 filters and the next 2 having 128 filters. The kernel size is 5 by 5, first 3 having strides 2 and the last one having stride 1. When the input image of size 28 by 28 by 1 is passed through the first convolutional layer with stride 2, the image becomes 14 by 14 size. This image is passed through ReLU activation and dropout layers. Next, this image is passing through second convolutional layer with stride 2. Then the image becomes 7 by 7 size. This image is passed through ReLU activation and dropout layers. Similarly, the image passed through third and fourth convolutional layer also. Next, this image is applied to flatten layer to flatten the image. Next, it passed through dense layer. The response would be 1 for the 2 image and for the generated fake image response would be 0. And now let's see the architecture of generator network. It consists 4 convolutional layers with different filters, 2 upsampling layers, 1 reshape layer and 1 dense layer. As I have already explained all these layers in the previous tutorials except upsampling layer. Let's see what is upsampling. This upsampling layer used for doubling the width and height of the input tensor. This simply repeats each row and column of its input in order to double the size. It is a similar idea to convolutional transpose layer, where the image size also doubles by inserting 0 values in between pixels before performing the convolutional operation. Both of these methods, upsampling and convolutional transpose, are acceptable ways to transform back to the original image domain. And both these methods may be tested in your own problem setting to find which produces better results. Some research has been shown that convolutional transpose method can lead to artifacts or small checkerboard patterns in the output image that spoil the quality of the output. However, they are still used in many of the most impressive GANs in the literature and have proven to be a powerful tool in the deep learning practitioner's toolbox. Again, it is suggesting you to experiment with both methods and see which works best for you. From latent space, 100 vector of length random noise is generated with mean 0 and standard deviation 0.02 from a multivariate normal distribution is being passed to the dense layer of 3136 units and applied batch normalization followed by ReLU activation. Next, it has to pass through a reshape layer to get the shape of 7 by 7 by 64. Now it is passed through the upsampling layer for doubling its size in both rows and columns. Next, it is passed via convolutional layer and applied batch normalization and ReLU activations. This is again passed via upsampling layer to get double its size and passed via convolutional layer batch normalization layer and ReLU activations. Next, it passed via convolutional layer, batch normalization layer, ReLU activations. Next, it passed via last convolutional layer and tanh activation function. Now the required size of image produced by this generator. To see this in action, let's start coding our GAN in Keras to generate pictures of animals. At first, we need a dataset for discriminator training for the real images learning. So we will use the camel numpy bitmap images file from Google's Quick Draw dataset and save it into the data and camel folder. For this, the link is given in the description. Also, this is crowdsourced collection of 28 by 28 pixel grayscale doodles. It is labeled by subject. The dataset was collected as part of an online game that challenged players to draw a picture of an object or concept, while a neural network tries to guess the subject of the doodle. It is really useful and fun dataset for learning the fundamentals of deep learning. Now we will start coding for module GAN model. Create a folder for models. In that, create a Python file gan.py. Importing the required packages. Random normal class is a layer weight initializer that generates tensors with a normal distribution by giving the parameters mean, standard deviation, and seed. These are the arguments. This is for instantiation of arguments. This generates multivariate normal distribution from latent space. This is the initialization of list for discriminator and generator classes. This is for activation method either leaky ReLU or ReLU functions. Now we will build discriminator model. The goal of the discriminator is to predict if an image is real or fake. This is a supervised image classification problem. So we can use the stacked 4 convolutional layers followed by a flattened and dense output layer. Here defining the input to the discriminator, the image should be in the size of 28 by 28 by 1. This for loop builds a stack of 4 convolutional layers on top of each other. Layer weight initializer that generates tensor with a normal distribution. This is batch norm. It is optional. If you want, you can use it. This is activation function. We use a ReLU function here. We have used dropout rate 0.4. Flatten the last convolutional layer to a vector 4 by 4 by 128 that gives 2048 units. This is dense layer of 1 unit with a sigmoid activation function that transforms the output from the dense layer to the range 0, 1 and initialized with normal distribution. The sigmoid activation in the final layer ensures that the output is scaled between 0 and 1 and it minimizes cost function. This will be the predicted probability that the image is real. This builds our discriminator model. It takes an input image and outputs a single number between 0 and 1. It is the required output. Now we will build the generator model. The input to the generator is a vector of length 100, that is z_time equal to 100, usually drawn from a multivariate standard normal distribution. The output is an image of the size, that is 28 by 28 by 1. Initial dense layer size 7 by 7 by 64. Layer weight initializer is used multivariate standard normal distribution. This dense layer consisting of 7 by 7 by 64 that gives rise to 3130 units. After dense layer, a batch normalization layer used. Next, ReLU function used. Next, it is reshaped to 7 by 7 by 64 tensor. It passed through 4 convolutional layers, the first two preceded by upsampling layers to reshape the tensor to 14 by 14, then 28 by 28, the original image size. In the third layer, we use batch normalization and ReLU activation. If you want to use leaky ReLU, you could also use. This is optional. If we want to use the convolution, we can use also. After every convolutional layers, we used 3 batch normalization and 3 ReLU functions used. After the final convolutional layer, we use tan activation to transform the output to the range -1, 1 to match the original image domain. Finally, this builds our generator model. It accepts a vector of length 100 as input and outputs a tensor of shape 28 by 28 by 1. Using this optimizer function, we can use either ADAM or RMS Prop Optimizers. The RMS Prop Optimizer restricts the oscillations in the vertical direction. Therefore, we can increase our learning rate and our algorithm could take larger steps in the horizontal direction, converging faster. This method for freezing and unfreezing the discriminator weights while training combined model. Now we will build the adversarial network. This is compile function for discriminator with binary cross-entropy loss. As a response is binary and we have one output unit with sigmoid activation. Next we freeze the discriminator weights. This does not affect the existing discriminator model that we have already compiled. It updates generator weights while training combined model. Latent space points taken as input is applied to generator for outputting images. These images is passed through discriminator, so its output becomes model output. We define a new model whose input is a 100-dimensional latent vector. This is passed through the generator and frozen discriminator weights to produce the output probability. Again, we use a binary cross-entropy loss for combined model. The learning rate is slower than the discriminator, as generally we would like the discriminator to be stronger than generator. The learning rate is a parameter that should be tuned carefully for each GAN problem setting. Now unfreeze the discriminator weights. Now we will train the discriminator with real images and fake images. For real images, it is 1 and it considers a valid. For fake images, it is 0 and it considers a fake image. One batch update of the discriminator involves first training on a batch of true images with response 1. Next function returns next item from the iterator. Then on a batch of generated images with response 0. It draws a random samples from a normal Gaussian distribution. Fake images generated by generator. For real images, discriminator loss and accuracy. For fake images, discriminator loss and accuracy. Taking average of discriminator loss for real and fake images. Taking average of discriminator accuracy for real and fake images. Now training the generator function. Generator trains the model with fake images as valid images. It draws random samples from a normal Gaussian distribution. One batch update of the generator involves training on a batch of generated images with the response 1. As the discriminator is frozen, its weights will not be affected. Instead, the generator weights will move in the direction that allows it to better generate images that are more likely to fool the discriminator, that is, make the discriminator predict values close to 1. The train method for training the discriminator on generator individually for calculating losses on weights. This is discriminator training and this is generator training. Saving the losses of discriminator and generator in the respective lists. to get the generator's generated images while running the model, saving the model weights. This is sample images function for generating fake images by generator. All these fake images will be saved in the run folder's gen_images folder. Clip function limits the values in an array. For every epoch, it saves 5 rows and 5 columns, that is 25 images. This function for plotting the models using GraphViz plots and saved in the run folder's GraphViz folder. This function for saving GraphViz plots in the respective folders. This save model function for saving the discriminator, generator, and GAN models in HDF5 binary data format, as it is a huge data. Now our GAN module is ready. Let's start building the GAN. Now open the Jupyter notebook and name it as GAN_camel_train. Importing the required modules, we will create these folders run in that GAN, in that 001_camel, in that GraphViz for plots drawing by GraphViz module, gen_images for generators images, and network weights for building the GAN model. The original NumPy camel dataset is scaled in the range 0 to 255 to denote the pixel intensity. For this GAN, we have to pre-process this dataset and rescaled it to the range -1, 1. And here is the function def load_pic drawset_camel. The downloaded dataset having some unwanted files or images, so we need to remove them from the dataset using these lines of code. This is for making the list for required images. Walk method generates the file names from the dataset directory tree by walking the tree either top down or bottom up. .ds_store is a desktop services store files. Their attributes of folder names or position of icons or choice of background images. It is created and maintained by the Finder application in every folder, starting with a full stop period character. It is hidden in Finder and many Unix utilities. For this programming, these files are not useful. So when you open a directory with Finder or when you walk the directory, you should ignore it. Now the separated files are appending to the list. 80,000 images are slicing from the dataset. It returns a random integer number. Now these images will be scaled to the range -1, 1, and all the 80,000 images sizes were reshaped to 28 by 28 by 1 using these lines of code. This loads arrays or pickled objects from .npy, .npz or pickled files, scaling each image to the range -1, 1, reshaping each image and its sizes to 28 by 28 by 1. This method is called when random state is initialized. It can be called again to reseed the generator. Next, we have to shuffle it. Next, seeding and shuffling. It returns the required images with labels. Using the above pre-processing function, we take camel dataset images as object x_train. Let's see the shape of training images are 80,000, 28, 28, 1. And the type of the dataset images are numpy.nd array. This is for capturing camel dataset images in the dataset_images folder. Now all the 80,000 camel images will be saved in the dataset_images folder. Let's see those images. Like this, all the images can be saved. It takes a lot of time to save all the images. So, for the time saving, I am just interrupting to move ahead. Let's check the images with index. Index number 0 on a 2D regular raster. Here 0 represents that the image data is scalar, so color map used for visualization of image. And you can see in the folder also, both the images are same. And we will see the last image 79,999. This is so total 80,000 images sliced from the dataset. Let's build the architecture. Using these parameters, our GAN model will be designed. We can see the discriminator, generator, and model summary plots are saved in the graphics folder. See here. Let's see here also the discriminator model. Similarly, generator model and the GAN model summary also. Let's give the training parameters. Batch size 64, epochs 4000. Print every n batches equal to 5 will produce generator images in the gen_images folder. Now start the GAN model training with the dataset and generator images. For every epoch, all the 80,000 camel dataset images are passed to the discriminator for training purpose. And after the completion of every 5 epochs, the generator saves its fake images in the gen_images folder. We can see here, at the initial stage, the generator produces this kind of images. After some epochs during training, it is clear that the generator is becoming increasingly adept at producing qualitative images to replicate the training set. It is a great thing that a neural network is able to convert random noise into something meaningful. It is worth remembering that we have not provided the model with any additional features beyond the raw pixels. So it has to work out high-level concepts such as how to draw a hump, legs, or a head entirely by itself. We can see that while there is some degree of similarity between the generated images and the training set images, they are not identical. And the GAN is also able to complete some of the unfinished drawings by adding legs or a head. This shows that the generator has understood these high-level features and can generate examples that are distinct from those it has already seen. Let's see the loss function of discriminator. The loss function is the binary cross-entropy loss between the output from the discriminator and the response vector of 1. The orange color plot is the generator loss. Green and red color plots are the discriminator loss for real and fake images. This discriminator loss is minimized by using sigmoid activation at the output of discriminator. Since the deep learning model is compiled to minimize the loss function, it would be natural to think that the generator loss function must be smaller. Then the quality of images will be produced. However, since the generator is only graded against the current discriminator and the discriminator is constantly improving, we cannot compare the loss function evaluated at different points in the training process. In this output, the loss function of the generator actually increases over time, even though the quality of the images is clearly improving. This lack of correlation between the generator loss and image quality sometimes makes GAN training difficult to monitor. Let's see the accuracy of our models. By observing this plot, the generator, which is shown in the orange color, its accuracy is lesser than the discriminator, which are in green, red, and black colors for real images, fake images, and average of both the images respectively. After a suitable number of epochs, the discriminator and generator will have found an equilibrium that allows the generator to learn meaningful information from the discriminator, and the quality of images will start to improve. Let's come to the conclusion. GANs are relatively new concept, and it still requires some research to reach their new potential. In particular, training GANs requires finding Nash equilibria in high-dimensional, continuous, non-convex games. The researchers should strive to develop better theoretical understanding and better training algorithms for this scenario. Success on this front would improve many other applications besides GANs. GANs are crucial to many different state-of-the-art image generation and manipulation systems, and it has the potential to enable many other applications in the future. Let's meet in the next tutorial. Signing off, Kishore Kumar Vajja from aiRobott.